Is my screen visible to all of you?
Yes, ma'am.
Yeah, okay.
Yes, ma'am.
Uh, yeah, yeah. Thanks. Sorry for the confusion. There's some issue with my camera of the laptop. So, okay. So I'm Sauravi. I'm currently doing my PhD here at IISc, and this is a TA-ship course that we are trying to do from NPTEL on electromagnetic theory. And so this is the first class, and this is a very introductory class where we'll talk about basic stuffs, basics of vector algebra and all that. Um, um, so yeah. Now, first of all, I would like to know what are the backgrounds of like you guys? Like, are you from like physics background, or like what kind of backgrounds are you from? That would just help me like take into account what I might have to detail in or not. There are too many people joining, and so I don't know who. Okay, yeah, okay. Recently visited Pondicherry, nice place. But like, what are your academic backgrounds? Uh, Engineering. Okay, okay. So, like, particularly if you have any like doubt or like, I would consider certain things that you already know. In case if you don't know, feel free to ask, and like I would try to detail it on that if needed. Okay. So let's get started. This, I think, if you are from engineering or from physics background, this will be a very preliminary course, and you'd be able to follow it quite easily. Uh, okay, let's get started. So to start with, this is an electromagnetic theory course, and if we is this issue happening this time? 1 second, guys. Sorry. Okay. So we know that there are, this four main kinds of forces. If we can talk about strong forces, which bind the which are there in the nucleus. Okay, so there are forces which bind the protons and neutrons, but these are short range forces. Then we have weak forces which are there in during radioactive decay, but these are also short range. So electromagnetic theory and gravitational electromagnetic forces and gravitational forces are some of are the two kinds of forces very fundamental, and they are long range forces. Now we know gravitational force is always there, but it gets more prominent when we have larger mass, right? So that's not very like obvious in all aspects. What is more, you can say, pertinent in regular day-to-day things is one of the most pertinent things is the electromagnetic force. Okay, and that's what we are trying to look at, how electromagnetic forces can result in different phenomena. That's what the course is about. Now, initially, to start with, electricity and magnetism were different concepts, separate concepts which were dealt with separately. And then as time progressed, Faraday, Maxwell, Lorentz, and all of them came in, and gradually we got to this idea that they are not separate concepts, but they are to be dealt together. They are intertwined with each other. And that led to this single subject of electromagnetism. Now, one concept of electromagnetism is quite important to understand, and that is this concept of field theory. Why? Because when we talk about, suppose if you have a collection of charges, okay, and then you want to look at how what happens because of those charges. So there they have an effect at a distance. So you can have a charge somewhere, and the effect can be at a location different from where it is, and it doesn't have to be in physical contact. Okay. So there is a action at a distance happening. And for that, what we need, like what came up as a formalism, is this field formalism of electrodynamics. So we would talk about fields and how one can characterize fields. Okay. So, and then as we proceed, we'll talk about radiation as well, where we talk about accelerating charges and how when a charge accelerates, it radiates. Okay. And how one can collect that radiation, what are the different aspects of antennas. And there are many aspects as we proceed in the course, we'll see. So to start with, we would look at how one can define field, what are the different phenomena that, or different, you can say, quantities that are used to define field. And for that, an important aspect would be vector algebra. Okay. So the very basic concepts of vector algebra is like, these are very well-known relations. We all know about it. Okay. Commutative laws, associative laws. I'm not going into this. Like, these are all trivial things. But normally we know what is a vector. It has a magnitude and a direction. And if you want to find the unit vector in a particular direction, what you do is, so if you have a vector, it would have this different components based on which direction it is in. And that would also, this is how you define a magnitude of a vector. And then if you divide the magnitude, like the vector with the magnitude, what you end up getting is a unit vector in that direction. Now, talking about fields. So there can be different kinds of fields. Okay. So one of, like, if you can break it into two major types. One is a scalar field. So what we mean by that is a field where the quantity only has magnitude. So if you talk about a region and how does the temperature change in a region, so there it doesn't concern us about, like, there's nothing like direction of temperature, right? So what matters is the quantity or the magnitude. So then it becomes a scalar field. While you can have quantities which have both direction and magnitude, like you can, velocities, displacements, and all that. And these are vector quantities. Now, a vector quantity will have a magnitude and a direction, and then you can have this different operations with vectors. So you can have a dot product, where if you have two vectors A and B, this is how you define the dot product, or you can have cross products, right? These things are like very fundamental things, and there are many relations which I'll come to, and those will be very useful as we work out the different laws and proceed in the course. So now if you have a field, okay, either a scalar field or a vector field, okay, so how do you define it, or how do you characterize a field? Okay, so there comes this different operators. So you have this del operator, which is given by like in the rectangular coordinate. This is how you would define it. Okay, del del x I cap plus del del y j cap plus del del z k cap. Now this operator can be used in different ways depending on what kind of field you have, and then accordingly you can get different information out of it. Okay, so suppose if you have a scalar field and you apply this operator on this scalar, what you end up getting is another new vector. Okay, and this is what, so if your phi is your scalar field, then when you apply this del operator on phi, what you get is gradient of phi. Now, what does this quantity tell us? So this physical understanding of this operators is very useful and very important. So when you have a scalar quantity, you apply this del operator, you find the gradient of the scalar. What you are actually finding is the change in phi. So del phi gives you the direction and along which phi changes the maximum. Okay. So now suppose you want to find how this quantity changes in any particular other direction. Okay, so you have a vector A, you want to see what is the change of phi in the direction along A. What you do a dot product of gradient of phi with A. Okay, and that gives you directional derivative of phi in the direction A, which means how is phi changing in the direction A. Del phi by itself gives us the direction where the maximum change in phi is happening. And then once you take a dot product with some other vector, it gives us the change in that direction. Okay. So this is how one can characterize a scalar field using the gradient operator. Now, when you have a vector operator, a vector field, so how do you use this del operator? So you use this divergence or curl. Okay. Now, what does divergence do? So basically, you're doing a dot product of this del operator with your vector, and you end up getting a scalar quantity, right? Now, this quantity tells us how the field lines emanate from a point. So suppose if you are at a point and there are different field lines, whether the fields are starting from that point, coming to that point, or there is no such direction inward, how do you get that information out? So you use the divergence. Okay. While what does curl tell us? Curl tells us about how is the field lines rotating. Okay. So if you talk about flux, then there this operators will come in. So the curl operator is basically just so you do a vector product of your del operator with v, which is your vector. Okay. And you end up getting another new vector. Okay. Now, these are the main operators. Now you can have different formulas involving this. Okay. And out of this, like many of them, you might have to remember, or these things will come quite handy as we proceed in the course. So suppose like this one, or like the last one, like as you work out, you'll see that you have to remember some of them, or you can also try to derive, but you have to remember them because they'll be very much useful. Now, let us talk about coordinate systems for a while. So we have discussed how fields can be and how one can characterize the field, how to use the different operators. We have done that, the basics. But now, when you define a vector or any quantity, we have a origin, we have a coordinate system, right? Now, in general, we talk about rectangle like x, y, z, x-axis, y-axis, z-axis. But that's not necessarily required. You can have different kinds of coordinate systems, right? You can have radial coordinates, like you can have spherical coordinate system in 3D. You can have cylindrical coordinate system. So the point is the expressions or the components of the vectors would change as we move from one coordinate system to another, right? So how do we relate that? So this is one such question where you are given a vector in the rectangular coordinates, and you are asked to find how it will look like if we go to the cylindrical coordinates, right? So you want to find the components in the cylindrical coordinates. So how do we proceed with it? So as of now, do you guys have any idea how to do it? Like, what are your thoughts in it, in this direction? Like, what is the basic protocol, or what comes to your mind when you see this question? Any idea? If you want to say something, you can unmute and also say.
That part is not covered in this week's lectures. I think it will be part of the second week.
Okay. Okay. Like as far as I saw the last year's courses, like there were questions in the assignments. I think in the last years where you had this kind of coordinate transformations. But anyways, so we'll try to see how to do it. Okay, and this would be very useful whenever you talk about, like, it's quite fundamental in a sense that you can use it in different aspects. But talking about electromagnetic theory, when you talk about how you represent a field or any vector, okay, so suppose you want to represent an electric field, it might be useful for you to represent it in a particular coordinate than other. Okay, so based on the symmetry that is there in your system, you might decide that cylindrical coordinates is a better way to represent than maybe the rectangular coordinates, right? So in those cases, you must know how this very idea of different coordinate systems came up and how one can relate from one coordinate system to another. Okay. So let's proceed. If you have any doubts, please feel free to ask. So basically, we know that, if you have rectangular coordinates, we have this x, y, z. And now if you have any function or any like, yeah, yes. Okay. So suppose if you have a vector and you know the coordinates in x, y, and z, okay? Now you want to move to another coordinate system. So you can say that basically you know that x can be written as a function of this new variables u1, u2, u3, similarly y and z. Okay. Now you want to find how you can write. So from x, y, z, you want to go to u1, u2, u3, where u1, u2, u3 will again be a function of x, y, z. So you want to have this transformation, right? Now, to deal with it in a more general way, let us talk about curvilinear coordinates. What it means is, so when you define a coordinate system, not necessarily always you'll have coordinates which are, straight and like rectilinear, right? You can have curvatures. Suppose if you have these three surfaces as you see here. So one is a surface where like u1 equal to constant. This is one surface, u2 equal to constant is another surface, u3 is equal to constant is another surface. Now, when these three surfaces intersect, you get a point, and now these three surfaces can result in a different coordinate system, right? So if where these two surfaces intersect, you get a line. So you can say where u2 curve and u1 curve intersect, you get the u3 curve line. Similarly, you have a u1 curve line, you have a u2 curve line. So now you have these three curve lines. And suppose if you have some point, some vector, okay, you want to represent it based on this coordinate system, okay. So basically, we are asking the question that if you have the xyz coordinate and you had a point P, now if you have a different coordinate system where you have this curved surfaces, how do you describe this quantity, this vector P? Okay. So for this, what we can do is basically consider that the point P has the position vector in the rectilinear coordinates given by xi cap plus yj cap plus zk cap, right? Now, here you can have these three curved lines, which are basically intersections of the surfaces. Now, what you can do here is you can draw tangents to each of these curves, right? Basically, what I'm telling is you can have a tangent along this line, you can have a tangent along this line, you can have a tangent along this line, right? Sorry. So how do you define the tangent? Tangent is nothing but you look at how your vector changes along this line. So basically, del u. So suppose if you take the tangent in the direction in this direction, right? Along the u1 curve. So along the u1 curve, your u2 and u3 do not change. Okay. So basically, you're looking at the change of r with u1, right? So what you do is you do this partial derivative of del u, del r, del u1. Okay. And you want to find the unit tangent vector, so you divide by the magnitude. So what does this give you? This gives you the direction of the tangent, unit vector in the direction of the tangent, right? Along this line. Similarly, you can do it for all the two other curve lines as well, right? So each of this tells you basically how your position vector or how your the position vector, how does it change along these three curve lines, right? So you have these three quantities like the magnitudes, which we call the scale factors, and the unit vectors are called other directions. Okay, E1, E2, E3, these are the unit vectors in that direction, in the tangential direction. So now what you want to write is you have a, suppose some, okay, dr differential where you can write it as del r del u1 du1 plus del r del u2 du2 plus del r del u3 du3, right? This is how you normally define a differential. So now if we try to substitute, what is this? This is same as what we had done before, right? So this is same as finding the tangent along this curve. So you write it as h1, which is your scale factor in that direction, into E1. E1 is your unit vector into du1. Similarly, you do it for the other three directions. So now what you are doing is basically now you are representing your position vector, but in terms of new quantities, which are u1, u2, and u3. Okay. So here, if you want to suppose have a define an arc length. So basically what you want to do is you want to find the magnitude of your dr, what is the magnitude. So what do? You do dr dot dr, and that gives you a quantity which is basically the distance or the arc length of your vector. Okay. So in each direction, basically now you can get the individual components, right? So in one direction, if you have the scale factor as h1 and du1 is your change, so h1 into du1 is your differential of arc length along this u1 curve. Similarly, you can have along u2 and u3. Okay, so these are the three differential arc lengths along the three new curves or new coordinates systems, right? So you can also define a volume element where you just do this product, and here you can try to solve it. So when you do this, it comes out to be 1. Now here, important point is, so what will this give you? This will basically give you the direction between. So whenever you do e1 dot e2 or e2 dot e3, that's basically the direction, the angle between this curved surfaces. It can be 90, it might not be 90. If it is 90, then it's an orthogonal system. If not, then it's not an orthogonal system. So typically, we when we talk about rectangular coordinate systems, these are orthogonal systems, but not necessary that always you will have coordinate systems which are orthogonal. Okay. So now what you can do is you can basically define your gradient, divergence, and curl, which were your operators. Okay. So you can define them. You can define them in terms of this new scale factors that we found, okay, and the new unit vectors, right? So if this is the general most way of defining this, you can say, what do I say? Defining this operators in different curvilinear coordinates. So based on your coordinates, your h1, h2, h3 will change, and based on your coordinates, your e1, e2, e3 will change. So you can use whatever coordinate system. Okay. So if you have a cylindrical coordinate, this is how your scale factors will be. Okay. And your obviously e1, e2, e3 will be rho cap, phi cap, z cap. Similarly, in a spherical coordinate system, your scale factors will be given by these relations, and the unit vectors will be r cap, theta cap, phi cap, right? And now if you put it here, you can find expressions for any coordinate system. So how do we find in this scale factors? This is what is the question, and this is what we just understood, right? You have to follow this process. Basically do the partial derivatives and find unit vectors. Okay. So now let's come back to the question that we had started with. So if you have a vector like this, we want to move from rectangular coordinate to cylindrical coordinate, right? Now in a cylindrical coordinate, we know how the coordinate system, how the parametric equations are, right? So we know that in x and y, if you have a cylinder of some radius rho, you can define the x coordinate as rho cos phi, and the y coordinate as rho sin phi, and then you have a z. So these are your parametric relations. Okay. So now what you can write is, suppose if this is your r, okay, so you represent r like this x, y, and z in terms of rho and phi. And still now your I cap, j cap, k cap remains. Basically, you have to now change this I cap, j cap, k cap to phi cap, rho cap, phi cap, z cap, right? That's what we want to do. So for this, what do? We find tangent vectors to rho, phi, and z curves. Basically, what we do is del r, del rho, del r, del phi, del r, del z. Okay. How do we do del r, del rho? Basically, just looking at this and doing the partial derivative. This is what you get, right? If you do a partial derivative with respect to rho. Similarly, you can do a derivative with respect to phi, and you can do a derivative with respect to z. Okay. So these are your, like, the magnitude of this, basically this factor is your scale factors, right? So this comes out to be 1, this comes up to be rho, and this is also 1. And when you divide this vectors by the magnitude, what you end up getting is the unit vectors in the direction of rho, phi, and z. Okay. So that means this is your rho cap, this is your phi cap, and this is your z cap. Okay. So now you can solve these relations to write I cap and j cap. See, z cap remains same for a cylindrical coordinates. Z cap is not changing. So basically, you can just replace k cap as by ez, right? But you have to replace I cap and j cap in terms of E rho and E phi. And for that, you can try to solve it from these two relations. Okay. So this gives you how one can write I cap and j cap in terms of the new unit vectors, which is your cylindrical coordinate system. Okay. And then once you know this, now you have to just replace, right? So you replace whatever vector you had, replace I cap, j cap, k cap by these relations that you just derived, and replace z, 2x, and y using this parametric forms. Okay. So once you do that, what do you get? Now you get your components of the vector in terms of your phi, rho, and z. Okay. So this is you end up getting. So you can now rewrite this vector as a rho into rho cap plus a phi into phi cap plus az into z cap. So that will be your vector in the cylindrical coordinates. Okay. I hope it's clear. So in this kind of question, so there can be many questions like this. Okay. So suppose if it was spherical coordinates, what do you do? So your parametric forms will then change, right? So you have to use this parametric forms x, y, and z. So that would change. Now, once you put that, you have to do this partial derivatives. So that will give you how your old and new unit vectors are related. So that will tell you how you can write I cap in terms of phi and theta, and similarly j cap. And then you replace it and you would get the new components, right? So that's how you can do it for any vectors, any coordinate system. Okay. So suppose if you have questions like this, so where you are given a vector at some point, okay, and you have to change it to cylindrical coordinates, right? So this is similar to what we just discussed. What do you have to basically do? You have to replace, because see, now this components are all constants. So you don't have to change anything here. Basically, you just have to change your unit vectors, right? X cap, y cap, and z cap. This you have to represent in terms of r, phi, and z. Okay. So based on what we had just discussed, can you try to solve it? I'll give you some time. Please try to solve. And if you are stuck somewhere, please feel free to ask. Okay. So basically, this is your question. You have to change x cap, y cap, and z cap because all the other components are just constants. So try to look at this and get an idea. Okay. So it's similar to what has been done here. Okay. You just have to replace I cap, j cap similarly as done here. Okay. So it's already like solved here. Just you have to look at it, find it, and try to do it. Okay. Like while looking at it, can you tell me which relation has to be used? Any idea, guys? Are you stuck somewhere? If there's any doubt, please feel free to ask. Question 10 minus 8, 6. These are your components. You have to change x cap, y cap, z cap to r cap, phi cap, z cap, right? So based on what we had solved and discussed here, can you tell me which relations to use?
Ma'am, to find rho, we have to find the modulus of R vector. Then for phi, we can tan inverse Ry by Rx. Then by using the equation 1, 2, and 3, you can get the unity vectors.
Right. So that's what we exactly. So basically, see, this is already solved for this cylindrical coordinate. So you already have the relations, right? The relations would be this. So this is your x cap, this is your y cap, and this is how they are written in terms of rho cap is nothing but r cap, right? Phi cap, like E phi is nothing but phi cap. So this is the relation basically, right? And Ez is z. This is same. So that means if you replace x cap by this relation, if you replace y cap by this relation, okay, and z cap remains same, that's what you have to do here, right? And how phi will be, that will come from this constants. That you are absolutely correct. Clear, right? So basically what I'm trying to say is that you have f of like fx I cap, fi j cap, fz k cap. This is what you have to cap, fi I cap, fz z cap, right? Now you can try to write a transformation matrix and try to write it in terms of vectors like this, where you know the coordinates in one system. You want to find this, and these are the transformation matrices. How do you get this? See, cos phi, sin phi 0, minus sin phi, cos phi 0, 0, 0, 1, right? How do you get here? This is same as this, right? Cos phi minus sin phi, and z remains constant. So there is no change. And then you have sin phi, again cos phi, right? That's what has been just put in the matrix form, right? So this is your transformation matrix for going from rectangular coordinate to cylindrical coordinate, right? So now once you do that, you get relations like this, okay? And you have to find phi. How do you do it? So that is same as what you just said. So you have to find the ratio of your y and x components and find tan inverse and find the relation, okay? And once you put the value of phi, you can try to find this components, right? So this is what you end up getting. Is that clear to all of you? Clear, right?
Yes, ma'am. Yes, ma'am.
Okay. So if it was not constant, if it was some other expression, then you also have to change that expression based on this relations, right? Based on the parametric relations, which is how do you change x, how do you change y, and how do you change z. Because these were constants, we had not changed anything. We did not have to. But if there were some expressions like the question, like in question here, you have to change according to the parametric relations. Okay. Now, how do we prove that the cylindrical coordinate system is orthogonal? So what do? We proceed using the similar methods. We want to find the unit vectors along the three new axes, which is your rho, phi, and z. Okay, and these are the unit vectors. And then we can use the typical knowledge of vector, analysis. So we do the dot product. If the dot product comes out to be 0, as you can see here, all the pairs, that means these are all mutually perpendicular. If not, then they are not perpendicular. So it's not an orthogonal system in that case. For cylindrical coordinate system, it's an orthogonal system, and that's why you get all this dot products as 0. Okay, so there can be different kinds of questions. Any random coordinate system one can design and can ask you whether it's orthogonal or not. In those cases, this is how you proceed with it. Okay, and remember, this is how you find your and this is how you find your scale factors, right? These three scale factors for the cylindrical coordinates is nothing but the magnitude of this del, like this tangent vectors. Okay. So now you have spherical coordinate systems, which will be very useful all throughout the course, because there'll be many cases where you would have spherical symmetry, where you would try to use the spherical polar coordinates. And there, this is how you would represent x, y, and z in terms of r, theta, phi. Okay. And if you want to write the vectors, you would need how to write r. Sorry, you would not, like you have to represent the old vectors, old unit vectors in terms of the new unit vectors, and these are the relations that you have to use. Okay. And then this is how you can define, line elements, or you can define the different operators. Okay. So basically, see, one can try to learn this, but you don't have to. Okay. Because there can be different coordinate system, and this can be difficult to actually remember all of this things. You don't have to remember. What you have to remember is how do we get to the scale factors, which comes in here, right? These are all the scale factors that are coming in, as you can see here, right? The coefficients at the front is coming from the scale factors. So if you know how to find the scale factors for your coordinate system, okay, and if you know the general this, right, then you can basically find your expressions for gradient divergence and curl, or any such operator in any coordinate system. Okay, the Laplacian is also very useful, as you will see, and this is how you can have different expressions in different coordinates. Now, let us start now. Like, we have briefly discussed about vector algebra, we have discussed about the different coordinate systems. So now let us talk about electrostatics to start with. And all of us already know about the basic Coulomb's law. It tells us how, if you have a point charge, and then if you have a test charge, what would be the force on the test charge because of the point charge. And this is the relation that you get, right? This is the basic Coulomb's law. And here this R vector is basically the separation vector between the test charge and the point charge. Now, it follows the superposition principle, so you can have different charges, and so in that case, you just sum up the effects. Okay, and this is my pointer one. This is the kind of expression you would get. Okay, and if you don't have discrete charges, but if you have a distribution, then you have to go from summation to integration, right? So if you have a line element where the charge density is given as lambda along a line, so in that case, you can define an integration like this, where you define a charge element given as lambda dl. For a surface charge, if your surface charge density is given as sigma, you can define your charge element to be sigma dA. Okay. And similarly for a volume, if you have the volume charge density as rho, then rho d tau. D tau is your volume element, dA is your area element, dl is your distance, the position element. So if you do rho d tau, that is your charge element in the volume charge density. Okay, and so in that way you can represent the same Coulomb's law either in terms of discrete systems or in terms of a continuous charge distribution. Okay, now you can use this relation to find fields for different configuration of charges, and these are very standard problems that one can do. Okay, the basic idea is, what do we do is, if you are said that if you have a charge distribution like this, and you have to find the field because of the charge this line of charge at some point p at a distance z. How do you do it? So first you define a charge element. You say that the charge per unit length is lambda. So lambda dl is your charge element, right? Now for this charge element, you want to find what is the field at this point. Okay. So for this, you need the distance between the two. Always for these questions, one have to be careful about the components in the question. So if you want to find what is the field in this direction, so what would happen here? Because of this, you would have some force, suppose, right? Now you can break it into these two different components. So when you have to write vectors, you can be careful about what component to choose. Okay, in many cases, because of symmetry, some components will turn out to be 0 quite easily. So look for symmetry in the system. And then what do you have to do? So you know the position, you know the charge elements, you use the Coulomb's law, and then you do an integration based on the length. Here, for this case, you have to do an integration from 0 to L, right? So basically what I mean is something like this. So you take a charge element lambda dx. So this is your dq. Okay. R is the distance from this element to the point where you want to find the field. Now there you look for the z component would be the cos theta component. You will also have a x component, which is given as the sine theta component. Okay. If this is angle theta, which is at this point. So this is how you could define based on typical Coulomb's law, right? So 1 by 4 pi epsilon 0 lambda dx by r square, do an integration from 0 to L, the cos theta component for z and the sine theta component for x. How do you define theta, the sine theta or cos theta? That is just looking at this, right? You know this is z, you know this is x, so you know how to write r, root over of z square plus x square, and then you can find all expressions for cos theta, sine theta components, right? So this is what you end up getting. So you do the integration and you would get an expression for Ez and Ex, right? So this is typically how it will look. So in all this kind of questions, whenever you find an expression, it's good to put the limits and see if it is making sense. So here we know that if we are very far, so if Z is much larger than L, this will look like a point charge with net charge given as lambda into L. So we can see if we get back the same equation, and that's what we end up getting. So if you take Z to be much, much greater than L, you would see that your electric field turns out to be the field at distance Z for a point charge given as lambda into L, which makes sense, right? So always do this consistency checks whenever you are trying to do this kind of questions. Okay. Now there can be other types of questions like here. So here you have a square loop, okay, of charge, and you want to find the field at the point P. So you have to proceed through similar processes, right? We know how to do it for a line of charge. So now you have 4 such lines which are arranged. So here it's important to note for symmetry. So this already is telling you that because, see, for this you would have a field in some direction, which would again, you also have something on the other side. So this tells us that the basic symmetry of the problem tells us that in X and Y, there'll be no field. The field will be in the Z direction. Okay, so look for symmetry in the problem always. So here again, what you can do is do the similar things, but now your point is not at one side. Basically, you have your line on both sides of your test point. So you have your limit from minus L to plus L. Okay, and there'll be 2 components which will add up. So you can have 2 into cos theta, right? The other things remain the same, and only the Z component remains. So, and then you try to find how the field will be, right? So this is how you can try to solve for this question. Till now, we have not solved for this yet, okay? We are trying to solve for this where you have a line minus L to L. You want to find at point P what is the field. So this is what you end up getting. Again, you can do the consistency checks to get an expression for like at limits, larger limits, and see if it is making sense. Okay. So this is for along the same line. So you have a line of charge and you want to find at point P, you know the distance. Okay. But here the distance from the point of like the test point is not actually Z. The distance is this, right? So you have to do a modification. Basically, what you have to do is for this question, your L has to be replaced by A by 2 because that's how this question is. And the distance from the center of the edge to your point is not Z. It's basically Z root over of Z square plus A by 2 whole square, right? So that is the change you have to do. Rest all remains the same. So now your expressions remain the same. And once you find for one side of the like one side, you can do 4 into that to find the net field, right? So that's how you can basically try to solve it. One second. Okay, so that's how one can try to solve for electric fields at for different kinds of charge distributions. You can have things like this, where now you have a ring, okay, and you have charge along the ring. So similarly, what you can do is you can define a charge element as lambda dl, okay, and again, due to symmetry, you will have only the z components coming in. Now here, interestingly, when you do an integration, okay, so your line element, you have to do an integration over theta, which gives you the net circumference of the ring that you have. Okay. So when you do integration of dl, it's just 2 pi r, right? So that again makes things simpler. So you can get an expression of electric field in this way. Basically, it's the same thing. You have to solve the integration, put the correct limits, look for symmetry, and use the Coulomb's law. Now, there are other ways of solving it. We can use, like, we would later see that there are simpler ways, okay, like Gauss's law, where you don't have to do the integrations, okay, and that would gradually come up as we proceed. There can be cases like not a ring, but so you can have a disk, suppose. So then you have a area charge, like there's a sigma surface charge density. Okay. So in that case, what do? You basically break your disk into small rings of radius r and thickness dr. Okay. So you can say that you have multiple small rings with varying radius. Okay. So finally, you do an integration from 0 to r because your radius is continuously varying, and you have the small ring elements, okay? And you find the field for each of these ring elements similar to what we did in the last question, and integrate over the different varying values of r, that is your radius, to find the field for the disk. Okay? So that's how this works. So these are all straightforward things. Now, one can do an interesting check where if your r is much, much greater than z, okay, basically you have a large plane. So there you end up getting the field for an infinite plane, right? Later, again, you can use, like when we talk about Gauss's law, you'll see that there are also other ways of deriving, getting to this point, okay? And if you go to much larger distances, this would look like a point charge. So again, you would get an expression similar to what we get for a point charge. Now, basically what we are going is, see, we talked about line charges, we talked about surface charges, okay? So you can also have spheres where you have a surface charge density, okay? Then again, you have to take a surface charge element and find the distance, okay? So the interesting thing, or the thing that one has to practice if one has to work with Coulomb's law, is how do you take these elements? How do you find the distances? How do you look for symmetry, okay? So a small element here would be given as r square sine theta d theta d phi. That's your area element for spherical coordinates. Okay. And then you multiply by the surface charge density. So that gives you the charge element. Now you can use this relation to find the distance from the charge element to the test point, and then apply Coulomb's law to do the integrations. Okay. So here again, you can see inside, because it's a uniform surface charge density on a sphere, inside the sphere, there is no field. Okay, so this has huge implications physically, which what it is telling you is that if you have a sphere with all the charge on the surface, inside there is no field. Okay, all the field is outside. So now there can be, like, as I looked at different questions in the assignment, there can be questions like this, which are very trivial. So if you have a vector and you want to find the unit vectors, okay, in that direction, what do? You find the magnitude, which is nothing but square root of all the components square and adding them. And once you get the magnitude, you divide each component by the magnitude. So that is basically your unit vector in this direction. Okay. Basically this. So root over of 12 square plus 3 square plus 4 square, that gives you the magnitude. And then dividing each component by the magnitude gives you the unit vector in the direction of this particular vector. Okay. Now, there can be also questions like, suppose surface charge density is given. You want to find what is the total charge on the surface, and you know the dimensions. So basically, you know what is the charge per unit area, and you also can find the area because you know the dimensions. So now it's very trivial, right? So what is the area? Be careful about units here. Okay. So like here you have coulomb per meter square, here you have centimeter. So be careful about that. So what you can do is basically find the area, multiply by the charge per unit area, you get the net charge. Okay. These are very straightforward questions that I saw. There can be direct applications of Coulomb's law. Okay. So there can be applications like you have a point charge of some magnitude at some position, and then you have a negative charge, another charge at some other point of some given magnitude. You want to find the force on one charge due to the other. Okay. So here, one point you have to remember is what is the charge that is causing the force and on which point or which charge you are actually finding the force. Okay, because that would define the direction of the vector. So be careful about that. Rest is trivial. Okay, be careful about the direction of the vector. So basically what it is telling you is you have a R1 vector, okay, where you have Q1 charge, and you have a R2 vector where you have Q2 charge. Now it is said, what is the force on Q2? Okay, force on Q2 due to Q1. So you have to find R12, which is R2 minus R1. So R2 is your charge on which you have to find the force. R1 is the one that is exerting the force. Okay, so that is your direction along which the force on Q2 will act. Okay, so R12, not R21, right? If it was asked what is the force on Q1, then you would have to find the other way around, basically equal and opposite, but be careful about this direction. So now you know the two vectors, so you can find the separation vector between the two, do a subtraction. Okay, that gives you the vector or the direction of the vector along which the force is acting, and you can find the magnitude of that. Okay. So now you have to find the magnitude of the force. So you can directly use Coulomb's law, which is nothing but 1 by 4 pi epsilon 0 Q1 Q2 by R square. Okay, put in the values, and that gives you the net force. Okay, if you have to find the vectoral form, so this is your net magnitude. Okay, but if you're asked write in terms of components, what do you do then? So in that case, so this is your net force. Okay, so you have the net force there, and you have the unit vector. The unit vector comes from this, basically. The unit vector along R12 is your unit vector. So you know the vector, you know the magnitude. If you divide the vector by the magnitude, you get the unit vector along this direction where the force acts. And now you know the direction of the force, you know the magnitude of the force. So how do you find the component? You put that together, right? So this is your magnitude, this is your unit vector. Okay, and now if you multiply, and you would get the components, right? That's how you get the components. Okay, now based on our, like, few slides back, we had discussed about differential surface area and about curvilinear coordinate systems and how one can define, you know, arc lengths in a particular coordinate system. So that's what is being asked. So for cylindrical coordinate, how do you do it, right? So basically what they're asking is, if I go back at figure that we discussed, so what they're trying to ask is these things, right? So if I look at this, if I say what is the component along this, what is the component along U2? So this is the component along U2. This is the component along U1. This is the component along U3, right? So that is what is being asked there for the differential. Okay. So if I go back, So if I go back, what it is telling you is you have, suppose a vector, some vector in the rectangular coordinates given as r, like I cap, j cap, k cap, xi cap plus yj cap plus zk cap. Now you write in cylindrical coordinates something like, dr r cap plus r d phi z cap, phi cap plus dz k cap. Okay, this is how you just write the different elements in phi and z components. So how do you define this differential surface areas? Once you find the dimensions of the arc lengths, you can just make a product of the two to get the area, right? So basically this. So you have H1, H2, H3, and you have du1, du2, du3. So you know how you can write the individual components. Now you do a product of the two. That would give you the area, differential area. Okay. So that means here, if you want to find the area element, basically this is what you want to do. Okay. So if you want to find an area along, suppose U1, like this surface, like the U1 surface, what you are doing is basically you are multiplying this, like the dimension along U2 and U3. Okay. So you get H2, which is the scale factor along U2, into H3, which is the scale factor along U3, and then the differential elements du2, du3, right? So here, what it means is now if you want to find along along the radial direction, so what you have to do, you will have two scale, like the scale factors. We know the scale factors for cylindrical coordinates, right? We had solved for it. We know that along r it is 1, along phi it is rho. Rho is your radius basically. So in this case it is r, and along z it is 1 factors. Basically this 1, rho is nothing but r for this question, and then again 1, right? So if you put in here, just use this relations, what it tells us, TSR should be equal to rho, which is h phi, into z phi, which is 1. So that means r should be there. And then you have du2, du3. What is du2? This is nothing but d phi. What is du3? That is nothing but dz. Okay, this is how this should look like. So this already tells us your answer should be this because others are not matching. Oh, is this matching? Yeah, this is also matching. So then you have to look for the other thing, like suppose ds phi. What is ds phi expected to be? H1, which is 1, H3, which is 1, du1 is dr, duz, du3 is dz, right? So basically this. And then dsz. dsz again tells us H1 is 1, H2 is r, which is your radius, okay? du1 is dr, du2 is d phi. So that tells you this should be your answer. Okay, so that's how you can find surface, like differential surface area. Similarly, you can also find volume where you multiply this 3 together, right? So that's how you can do it for any coordinate system. Okay. Now there was this question where it says, how does the electric field vary with distance in case of infinite line charge? So this is again, one can start from this point here. Okay. So you can do this integration. This is something we just discussed. So you can do the integration, take a line element, do integration from minus L to L. Okay. Take only the Z component remains because of symmetry. And this is the expression that you get. Now this is for a given finite L. Okay. Now for an infinite line charge, what you have to do is you have to replace L by infinity. So you do an integration. So now what you have to do, an integration is from minus infinity to infinity for this question. Okay. You don't have to use the symmetry. You can also use the symmetry, then it will be 0 to infinity. So if you do that integration, what you end up getting is basically this. Okay. Which tells us, so this is again this limit of L tending to infinity, which gives us this expression. Okay. So what this is telling you is the electric field for an infinite line charge is inversely related to the distance from the line, right? So the answer should be inverse relation. These are standard questions. We have been solving it like quite some time, but because that's how we are starting the course, so we started with very simple stuff. Okay, so the answer for this will be inverse radiation. Now again, there can be questions like this. So this is similar to what we had discussed, right? So here again you have a vector in the, so x cap, y cap. So that means it's in the rectangular coordinate system. We have to change to cylindrical coordinate system. So how do we do it? Can you try solving it? Basically, you have x, y, right? Okay, my phone battery is almost down. A second, guys. Okay. Yeah. So basically you have x, y. Okay. So what do? You replace x and y in terms of r and phi, right? And then you also replace x cap and y cap in terms of r cap, phi cap, right? So if you do that, can you tell me what the answer should be based on what we had been discussing in the course today? Can you just try to solve? Like you gradually have to get used to, like, doing this transformation, because like they'll come many times in different cases in your question. So it would be good if you just try to do it by yourself, because you already know the process as of now, right? Anybody can guess the answer, or tell how to do it, or can try solving it.
We have to just put the formulas for unit
Yes.
vectors and the scale factors.
I'm not
No,
able
we
to
have
hear
to
you.
use-
Can
We have to use the formula for unit vectors and the scale factors derived earlier.
Yes. So if you do that, what do you think the answer should be?
I have not memorized them.
No, try to solve it. See, so it's easy, right? So x, what is x? If you want to write it in cylindrical coordinates, x is nothing but r cos phi, right? What is y? Y is nothing but r sin phi,
Sin phi.
right? Now, how do you write x cap? If you try to solve, what do? You write the vector as, x I cap plus y j cap plus z k cap. You do the partial derivative, and from there you can try to find how x cap and y cap can be written in terms of r cap and phi cap, right? And we tried a question where we saw that there's this transformation matrix, which tells us that, you can write x cap as cos theta, or like cos phi I cap minus sin phi y cap, right? You had this transformation relations that we used in a previous question. So you have to do the same. Now, once you put that, you get your expression, right? So basically
Okay.
this, right? So you have replace x, replace y, there is no z. So this component can be written as r cos phi by r square. Y can be written as r sin phi by r square. And this is your transformation matrix that helps you go from x cap, y cap, z cap to r cap, phi cap, z cap. Okay. And so you would get the components in the cylindrical coordinates. So do the multiplication, and what's the answer?
Z is 0, so we can get it option A for r by r square plus pi cap by pi.
No. Okay. So do this multiplication, right?
Okay.
Z is 0. That is fine. So this goes away because there's no Z involved anywhere. So
Yes.
this is gone. Okay, very good. Now what are the other things? Like try to do the multiplication.
Okay.
So you get a cos square here, you get a sine square here. R, if you take common, cos square, sine square, addition goes to 1. So see, you can very well see that if you do a product of this plus this, like this term would be 0, az is 0. But what happens to the a phi term? You are saying this, right? But
Yes.
try to, yeah, but try to find a phi,
But
right?
if you do the inverse multiplication, we'll get r cap by r square, the last option.
Okay. R cap by r square. Okay.
Is last.
Basically, you're saying cos square. So r cancels
Mhm.
here. So you have a 1 by
Cancel.
r.
Yes.
And then you have cos square plus sine square, which
Fine.
is 1.
Yes.
So what do you get? Do you get r square?
I is r square only.
Okay, again, this r and this r square cancels, 1 r remains, right?
Yes. Then okay. R will come.
Yeah.
Okay.
Again, here you have minus. So sine phi, cos phi, minus sine phi, cos phi, sine phi. So this cancels each other, right? So that
Yes.
gives a phi to be 0. So a phi is 0, az is 0. In AR, just do the multiplication. Like be
Yes.
careful about doing it. Okay, so
Yes.
because your r and r, this will get cancelled. So you end up getting this. So 1 by r is your radial component. Now,
Okay.
in vector, remember you have to write it in vector form. So this corresponds to the, so the unit vector in the radial direction is r cap, right? So you
Yes.
write
Yes.
a as r cap by r. Yeah.
Okay.
So
Thank
that's
you.
how you can try to solve all this kind of question. There can be numerous such questions, but this is a typical way of solving it. I think that's all for today. Do you guys have any question particularly about anything?
Please go through that coordinate transformation once again, ma'am.
Okay.
That
I'll start
where
at the here, right?
you yes, ma'am. The general method to transform any coordinate system.
Yeah. So basically, for any coordinate system, will it be okay if I start with the, like, do the example, like explain the example, or do you want, like, okay, anything? Basically, what you have to do, see, you want to find how your particular vector, so what are the components? The component is telling you how much the vector is along that direction, or how much of it is in some other direction, right? That is what component means, right? So
Okay.
that means if you have a vector, you want to see how this vector is along the particular, axis, the different axes. So you want to find, suppose the vector is given as x I cap, y j cap, z k cap. So this is the vector. Then you want to find what is the change, or how does it vary along this one, or along this one, right? So for this, what do? You try to find partial derivatives. Why partial derivative? Because what is this line? So suppose if you look at U1 curve, U1 curve is the intersection of this surface where U2 is constant and intersection of this surface where U3 is constant. So along this line, U2 and U3 both are constant, right? So what is varying along this line? U1 is varying. So anything that, so if your quantity changes along this line, or how this quantity changes, will come from the partial derivative of your vector with respect to U1, right? So that means the unit vector along this direction will be given as del r del u1, right? You can find the magnitude in that direction. That will be your scale factor. Okay. Similarly, for the other two directions. So in each direction, you have a unit, like you have a tangent vector, which has a magnitude, which tells us how it is changing, how much is the change, which, and the direction, which are the normal vectors. So basically now if we just look at it and imagine your cylindrical coordinate system, what is the u1 curve, what is the u2 curve, and what is the u3 curve, right? So u1 curve is the, suppose, the radial curve, so along which your r is changing, right? The radial line. Then you have phi cap, so along which the phi is changing. And then you have z, right? Z cap. So that's how you can define the three directions, right? Basically, when you define a cylindrical coordinate system, how do you do it? So you tell that if this is your rectangular coordinate system, define, now you want to go to cylindrical coordinate system. So you define a cylinder, right? Based on, sorry, ignore my drawing. So here, how do you define it? So you say that there is, if you take an r vector, so this is your r, that's the radius. You have a phi, which is the angle, right? Z. These are the three components. How the any vector you are trying to represent it. So you want to see what is the direction along the radial direction, along phi, along the curved direction, and the z, right? So you have to find, that means you have to find whatever vector you have to do del r del like del vector. So suppose your vector is v, so v del r, then you have to do del v del phi, then you have to do del v del z. That will tell you is the change in this, along this line, this individual. And if you do a unit vector, divide by the magnitude, you get the unit vector along this direction. So this is nothing but r cap, phi cap, and z cap for cylindrical coordinates, right? So that's what has been done here. So basically, if you have a position, suppose, where the components are x, y, and z in the rectangular coordinate. So what you do, you have a relation between x, y, and z from rectangular to cylindrical, which is the parametric form, right? X cos theta, r x cos theta, x sin theta, all that, r cos theta, sin theta, z. So that is there. Now, once you write this, so this is your vector. Now you want to see how your vector is changing along the radial direction. How is it changing along phi? How it is changing along z? For that, you do the partial derivatives. Clear?
Okay.
This gives you the tangential vectors. So this vector by itself has the magnitude of the change and the direction of the change, both, right? If you do a
Okay.
unit vector, that just has the direction. So this by itself is nothing but your rho cap, right? This is nothing but your phi cap. And this is nothing but z cap, right? And this magnitude tells you what is the change along rho, along phi. So that these are the scale factors. Like, I mean, how it is changing when you go from cylindrical, like rectangular to cylindrical. What is the scaling? That comes from the magnitude. So here this is 1, this is rho, and this is again 1, right? So once you know the scale factors, which is h1, h2, h3, and you know the unit vectors, which is e1, e2, e3, now what you can do? So now you can do all these kinds of relations, right? So basically, so if we look at this relation, what is this? This is nothing but, so in rectangular coordinates, you would have del phi del x I cap, del phi del z y cap, del phi del y y cap, del phi del
Ma'am,
z
where is
z
your
cap.
pointer, ma'am? I cannot see.
Oh, okay, sorry. This is just the pen. So I mean, this one, if you have to write, so for rectangular coordinate, your h1, h2, and h3, all of them are 1, right? Scaling is 1. And e1, e2, e3, these are x cap, y cap, and z cap. That's your rectangular coordinate system. Now you want to go from rectangular to some other coordinate system where there is a scaling. So there now for the, suppose for the cylindrical, we just derived that the scaling is h rho, h phi and hz, which is 1 rho and again 1, right? So once you, yeah, some network. So once you get that 1 rho and 1, so what do? Now you can replace it here, right? So this is 1. So this you will, so for cylindrical coordinates, what do you get? You get del phi del r into r cap or phi cap, rho cap. Again, you have plus 1 by h2, where h2 is rho. So 1 by rho del phi, 1 by rho del phi del phi. Sorry. Can you please unmute if you don't want to say anything? Yeah. So basically, then you can put 1 by h2, which is rho here, and then you have del phi again and phi cap, right? Similarly, you can have for the z. Z again h3 is 1, so you have del phi del z, z cap, right? Similarly, you can just put in all these scale factors wherever they are there, and u1, u2, u3 are the what do I say? The variables rho phi z or r theta phi. These are your u1, u2, u3 basically. Is it making sense? Hello?
Yes, ma'am.
Understood, right? So if you know this, then you don't have to remember this relations. That's what I meant. So basically, all this is just coming here, whatever you are getting is just by replacing the correct scale factors and this unit vectors in the general expression. Okay. If you just remember that, you can derive this, or you can do it for any coordinate system, not just spherical or cylindrical. Okay.
Okay.
Yeah. Any question, anyone? Any other question? Okay, so if not, let's call it a day. Thank you. I'll just find my thank you slide. Yeah, thank you.
Thank you.
Thank you.
ma'am.
Yeah. Thank you, guys.
Thank you, Sarvi.
Thank you.